All right, this is question number 33, and it says a professor wants to know if online homework improves his student grades on the final exam. He randomly selects one class that uses online homework and one class that does not use online homework, both in the same subject. At the end of the semester, he summarizes his findings. Okay, so he has here the class with online homework and one without, the number of students in each, the mean final exam score, and the standard deviation. So what we notice here is that we're talking about two means, and they are independent, because you have one class which is just online homework, and then you have another class without online homework. One is not dependent upon the other one. So two different samples of two different classes. So this is going to be two independent samples. So let's see here. This is going to be two independent means. And so it says, write out the null and alternative hypotheses necessary to test at a 5% significance level if online homework improved the mean student grade on the final exam. So my null hypothesis and my alternative hypothesis. Okay, well, when we're comparing two different means, mu1 equal to mu2 is what we want to set up as our null hypothesis. And we need to decide which one is going to be our alternative hypothesis. So what did it say? Let's see. Let's call online homework. Well, maybe let's just call this sample 1. Sample 1. Sample 2, right? And so we want to know, what does it say? He wants to know if online homework improves the student grades on the final exam. So in other words, we want to know if the grades in the online homework were better than the without online homework. So we're going to say we want to know if mu1 is greater than mu2. Okay? And let's see, it does state that alpha equals 0.05. I guess we should go ahead and comment on that. Okay, now it says use the computer output to answer the questions. The test statistic is, well, that's going to be your t, and I'm going to put that as 1.795, and your p-value, which is 0.0395. Okay. Let's see, I did my test statistic there, and then my p-value there. Okay. What conclusion should be made about the null hypothesis? Well, let's see here. If my p-value, which is 0.0395, is less than 0.05, so if p is less than alpha, then that means that we are going to reject the null hypothesis. Reject the null hypothesis. Okay. And let's see. Reject the null. What conclusion? I guess that's all we need to state there. What conclusion should be made about the alternative hypothesis? We will support the alternative hypothesis. Or I guess I could say, I'm just going to say support H1 alternative hypothesis. Okay. And then final conclusion. Does the sample provide enough evidence to support that online homework improved final student grades on the final exam? Well, let's see. We said we were going to reject the null hypothesis. That means that we are supporting our claim that the online homework does improve student grades on the final exam. So we would say, yes, the evidence supports our claim that online homework improves grades on the final exam. Okay. Now it says a 90% confidence interval for the study was 0.37 to 11.03. Use a 90% confidence interval to determine on average how large of an increase in final exam grades. I should probably say grades, huh? Do we expect to see from using online homework? Does this look like adequate justification for using online homework? How can the study be improved? Well, let's see here. What we're saying is, how large of an increase in the final exam grade do we expect to see from using online homework? Well, it's going to range anywhere from 0.37% to 11.03. I guess maybe, I don't know if I want to say percentage points, but I guess maybe we'll just say points. So, how do I want to word this? Let's see. So the output from our confidence interval is the difference. So in other words, we're saying that if we take mu1 minus mu2, right? So mu1 is my online homework minus mu2. We're saying that we're getting 0.37. So let me make a little note here. Mu1 minus mu2 is going to be anywhere from 0.37 to 11.03. So in other words, we're saying that, so my bigger one is the first one, right? So it's got a larger final exam score there, but it's only bigger by 0.37 to 11.03 points, right? That's what that means. And so, how would I put that in words? I guess I would say that the online homework's mean is higher by 0.37 points and is higher by, I guess, between 0.37 points and 11.03 points. Okay, so that's the first thing. On average, how large of an increase in the final exam? Okay. Does this look like adequate justification for using online homework? How can this study be improved? I would say no, this is not adequate justification. I mean, if your exam grade only improves by 0.37 points, that's really not substantial. Like, that's not even a half of a point. So this is not a substantial justification. However, if it does increase by 11 points, I mean, that is pretty substantial. And so, the question is, well, which one would be, enough of an increase? Well, we can't say. We don't know. It's somewhere between those two values. So I would say this is not adequate justification since 0.37 points is not substantial. Even though 11.03 points is. So not enough of an increase to justify this. How can the study be improved? Well, the sample size is pretty small to have enough information to decide. So to make the hypothesis test better, we just use a larger sample size. So I would say too small of a sample size. Use larger sample size to improve the study. Okay. Next, number 34. In the General Social Survey, random adult Americans were asked if they were healthy and if they are happy. Of the 2,569 people who claimed to be healthy, 2,499 also claimed to be happy. Of the 162 people who claimed to be not healthy, 123 also claimed to be happy. Test at a 1% significance level if the proportion of healthy adults who claim to be happy is higher than the proportion of unhealthy adults who claim to be happy. Okay, so let's see what we have here. We've got, let's see. First of all, it says proportions. Oops. Okay, so I know that I'm going to be using p's, and I'm comparing proportion of healthy adults who claim to be happy to the proportion of unhealthy adults. So it seems that I have two different proportions here. So this is two proportions. Okay, so let's see here. How can we decide null hypothesis alternative? Okay, so let's see. The first thing, let me write down my information here. So I have sample 1 and sample 2. Sample 1, let's see, it says random adults are asked if they're healthy and happy. Okay, so sample 1 is going to be my healthy one. Sample 2 is going to be my unhealthy. Okay. And so for my healthy ones, it says of the 2569, that's my N, 2569. And my X is 2499. Those are the ones that claim to be happy. And then the ones that are unhealthy, my N is 162. And the X there is 123. I guess I'll call this 1, 1, 2, 2. Okay. And our alpha is going to be 0.01. Okay, so we want to know, so sample 1, the proportion of healthy adults, so P1 equal to P2. And then here we want to know if the healthy adults is higher than the unhealthy. So P1 greater than P2. Those are lowercase p's, by the way. Okay, so let's find out what do we have here. Use the computer output to answer the questions. The test statistic is, well, in this case is the Z, so 13.463. My p-value is less than 0.001. So I'm just going to put is less than 0.0001. Okay, so that means pretty small. Let's do this. Test statistic. P-value. Okay. What conclusion should be made about the null hypothesis? Well, my p-value, let's just say it is 0.001, or it's less than that, is definitely less than 0.01. So since p is less than alpha, we reject the null hypothesis. So then we would support the alternative. Okay. Does the sample provide enough evidence to support that the proportion of healthy adults who claim to be happy is higher than the proportion of unhealthy adults who claim to be happy? Yes. It seems like it's significantly higher, right? So yes, the proportion of healthy adults who claim to be happy is Let me try that again. Significantly higher than the proportion of unhealthy adults who claim to be happy. Okay, a 99% confidence interval for the test is given here. Use this confidence interval to determine how much higher is the percentage of healthy people who are happy. Okay, so how much higher? Well, remember this is the difference, right? So we're saying P1 minus P2 is, let's see, greater than 0, right? Greater than 0 is what we have. So if P1 minus P2, proportion 1 is my healthy people, right? And so we're saying that healthy minus unhealthy, okay? This is how much higher the percentage is. So it's anywhere from 0.127 to 0.300. Maybe I'll just do this. Okay, so we would say that the proportion of healthy adults is who claim to be happy is higher by between 12.7% to 30%. Okay. This, let's see, what's the next thing? How does the confidence interval support your decision about the null hypothesis? I would say this agrees, because this would support Okay, since 0 is not in the interval, then we would reject the null. Let me say we would reject H naught. So it agrees with my decision about the null. Okay. All right. Next. Number 35. This is for 1 week in May. The Iowa Department of Agriculture reported the mean weight of Barrows and Gilt's young male and female hogs as 275.4 pounds. To check this claim, a random sample of hogs was obtained and each was carefully weighted. Weighted? I'm thinking that should be weighed. The weight in pounds of each is given in the following table, and several graphs of the data are provided. Okay, so we've got, here there are weights in this table. We've got a histogram over here, which looks to be fairly bell-shaped. We've got a box plot over here, which looks, approximately symmetric. Here we've got a normal probability plot, and it seems to be pretty linear, right? All those points are pretty close to that regression line. So I would say that everything is leading us to think that this is like a kind of a normal distribution here. So what are we wanting to do here? The claim is to check this claim. What is our claim? Okay, sorry. I mean to pause for so long, but I guess I don't know what we're claiming. Okay, well, I guess it's neither one, greater or less, was specified. So I guess we'll just say, are they different? Okay, so we're talking about means, right? Did give us the mean here. The mean weight is 274 pounds. Okay. So I see. So for 1 week in the Iowa Department of Agriculture reported the mean weight of these hogs as 275.4 pounds. But then to check the claim that that's what it is, we found a random sample of hogs to check to see if it's different. It didn't say more than or less than. Now I'm seeing it. Sorry. Took me a little minute. It is almost midnight while I'm doing this video. Sorry about that. I'm kind of tired. Okay, so the null hypothesis and the alternative hypothesis. So the null is where the mean would equal the 275.4. And the alternative would be that it's not equal to that. Okay. Which of the following requirements are met? Justify your answer. The sample is a random sample of data. Yes. C highlighted above. Let's highlight where it says random. Random sample. Okay. either n is greater than 30 or the sample data came from a population that is normally distributed. So I think that should be gone. Okay. Well, I was looking at all those things, and I pointed out that, yeah, I feel like this histogram, it looks approximately bell-shaped. The box and whisker plot is fairly symmetric. The normal probability plot, it gives you fairly linear, right? So all of these things indicate that it's coming from a normally distributed population. And our n is 2, 4, 6, 8, 10, 12. N is 12, so that's not greater than 30. But by looking at, so n is equal to 12, which is less than 30. But the histogram is approximately bell-shaped. The box plot is fairly symmetrical. And the normal probability plot is fairly linear. So normally distributed. Okay. So that's what I would say on this one. There we go. Is n less than 0.05 divided by capital N. Now what I have always given is this kind of like this. I say n divided by 0.05. So if we can calculate that, in this case 12 divided by 0.05 is going to be, let's see here. Sorry, let me go ahead and divide this out here. 12 divided by 0.05 is 240. So is 240 less than my whole population, which is like young hogs in the state of Iowa. Young hogs in Iowa. That would be a yes. Okay. So if sigma is known, you may use the normal distribution for the sample means. If sigma is not known, you may use the student t distribution for the sample means. Well, let's see here. Is sigma known or unknown? I don't think it was stated, right? No, they didn't give us a standard deviation. So we would say sigma is not known. So we would use the student t distribution. Okay. All right. Next. Number 36. Says use the scatter plot to determine the relationship between variables. So looking at these top ones here, I mean, I'm looking at over here on the left is a scatter plot, and on the right here you're seeing like a normal like a probability plot. And excuse me, I meant this was scatter plot. So we've got two scatter plots here, and looking at them, you see on the left that this is seems like a I don't know, moderate positive relation here on the left. And on the right, this seems like a very strong positive linear relation. They both show positive linear relationships, but on this graph over here, I would say that R is going to be a lot closer to 1, very close to positive 1. And for this graph over here on the left, I would say, again, your R is going to be fairly close to 1, but not as close as the one on the right. So reasonable guesses for the value of R might be 0.9 for the one on the left, and maybe even 1 for the graph on the right. I mean, this looks almost like a perfect positive linear relation. So I would say these are both linear, let me put positive linear relations. Positive linear relations. The graph on the right has a correlation coefficient R closer to 1. I would guess that R is 0.9 for the graph on the left. And R is 1 for the graph on the right. Okay. Let's see. Looking at the graphs here in letter B, these both look like they have negative linear relations. Although this is I guess this one up here I would call maybe a strong positive. This is almost a perfect positive, almost perfect positive. Down here, I would say this is like a moderate negative linear relation here on the left, and this is a strong negative linear relation here on the right. So I would say that if I had to make some statements here, perhaps, let's see. So these are both, okay. These are both negative linear relations. The graph on the right has a correlation coefficient R closer to -1. I would guess that R may be -0.8 for the graph on the left. And R would be -0.99 for the graph on the right. Okay. And looking at these last two, I would say that these have no linear relation. These both have no linear relation, and both would have a correlation coefficient close to 0. So this one here doesn't seem to have any relation at all, whereas the one on the right seems to have a parabolic relationship. It's not linear, so still you're going to get an R, which is close to 0. Okay. Next. Number 37, a random... I thought I only had 37 questions. I guess I have 38. Okay. Oh, man. All right. A random sample of multiple story buildings is measured in feet. Is there a linear relationship between the number of stories and the height of the building? All right. We will predict the height of the buildings from the number of stories. Based on this, which variable is explanatory and which is response? Explanatory variable is going to be your x. That's the one that's doing the explaining. And what is being predicted, that's going to be your response variable. That's responding to. So we will predict the height. So if you're predicting height, that's going to be your response variable. Predict height. Okay, so your explanatory variable, explanatory is going to be the number of stories. And the response, that's going to be the height. Okay. Let's see. Use the computer output to answer the questions. All right, we got a lot of information here. Now, I'm noticing this is different than what we were seeing on our calculator. On our calculator, we had y equals ax plus b, right? And so this looks different. So I really want you to kind of pay attention and notice this right here, that's different, okay? So just keep that in mind whenever you're coming up with any kind of equations here. Report the correlation coefficient and interpret. So correlation coefficient is R. Your R is equal to 0.895. Interpret. This would be, I would say, maybe a moderate positive relation. Maybe, I guess, strong. That's pretty close to 0.9, I guess. So I'd say this is... This indicates a strong positive linear relation. Write your hypotheses. So, this is something that we did not do in our class. For this kind of problem. We never talked about the population correlation coefficient. And so, yeah, I think I'll go ahead and state this here, but we did not do this in our class. So the null hypothesis is going to be stated as H naught. This is going to be rho. It's like, it looks like a P, but it's not really a P, which is the population correlation coefficient, be equal to 0. Your alternative is that there is, so you state the null hypothesis, and then the alternative hypothesis is that there is not equal to 0, okay? And so if rho is equal to 0, then there is not a linear relationship between the variables. So you're basically testing to see if there is a linear relationship between the variables using a hypothesis test instead of using what we did, which was looking at the critical value on the formula sheet. All right, report the test statistic and the p-value. Okay, so your test statistic here is going to be t. So we've done this before, right? So t is going to be 7.228. The p-value is 0.0001. And is there a linear relationship between the number of stories and the height of the building? So you can either check the critical value from your formula sheet to compare here, or you can use a hypothesis test. So what we did in class was we checked the critical value. We said, all right, so my R is equal to 0.895. And so my absolute value of R was 0.895. And then we checked, so my N, oh, that doesn't give it to us. All right, we can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So N is 15. Okay, so if N is 15 and we go on our formula sheet, let me see if I can pull that up here. Okay, so here's your critical values here where N is 15, and then you look over here that you see 0.514 is your critical value here. So we come back over here to our table. Let me say critical value is 0.514. And when you compare, you say, okay, my R is greater than my critical value. And so if R is greater than the critical value, then there is a linear relation. There is a linear relation. Now, if you wanted to go the hypothesis testing way, you would just check your p-value against an alpha, which we default to 0.05. In any case, p is less than any alpha that we would choose, and therefore you would reject the null hypothesis that your correlation coefficient is 0, and therefore saying that it is not equal to 0, thus there must be a linear relation. Okay, if possible, make the best prediction for the height of a 25-story building built in the late 20th century. So we need to come up with our y-hat equation, and note the formula here, right? It says A, so that's 151.2 plus your B, 9.726 x. A little bit different than what we are used to kind of seeing from our calculator output. So just wanted you to be aware of that. And so what we do is going to plug in the 151.2 plus 9.726 times 25. And we should get 394.35. So in other words, the predicted height would be 394 feet, right? That would be the best prediction that we have here. Make the best prediction for a height of a 0-story building. Okay, well, not possible. Not possible. You can't have a 0-story building. Okay. Okay. And our last problem. Number 38. The following data represent the total compensation for 10 randomly selected chief executive officers and the company's stock performance in 2009. The stock return in percentage is given on the top row of numbers, and the compensation in millions of dollars is given on the bottom row of numbers. The requirements are met, and the linear regression t-test results are below. Okay. Letter A, it would be reasonable for a higher stock return to lead to higher compensation. Now, what do we say? Stock returns. This is a stock return, and this is compensation. Okay, compensation, there we go. Okay, so it would be reasonable for a higher stock return to lead to a higher compensation. Based on this, which variable is explanatory and which is response? So stock return, well, sorry, this would be the explanatory. Explanatory would be your stock return. And the response would be the compensation. Okay. State the correlation coefficient and interpret. So correlation coefficient, that's your R. R equals negative 0.206. Okay. This is a weak negative linear relation between the variables. Weak negative linear relation here. State the test statistic and the p-value. All right, so your test statistic, t, is negative 0.596. The p-value is 0.5678. Is there a linear relationship between the stock return and the CEO's compensation? Well, let's see. If we compared the p-value, again, we would just kind of choose your alpha to be like 0.05. But in this case, you'd say p is greater than alpha, and therefore you would not reject the null hypothesis. So if you wanted to set up the, the hypothesis test, you could do that. We didn't talk about hypothesis testing with this stuff. And so what we did is we just looked at the R. And so our R, absolute value of R, is 0.206. And then the critical value, right? So N equals, what is our N? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our N is 10. Okay, and so our critical value is going to be 0.632. Okay, so when we compare this, the absolute value of R, well, here, let me do it like this here. Let's put 0.206 is less than 0.632. And so if your absolute value of R is less than your critical value, then there is no linear relation. Okay, well, that's it.